Across the universe, whether we observe galaxies that lie close to us or ones billions of light-years away, we consistently see the same characteristic scale in their distribution. By comparing how large this scale appears at different distances, scientists can measure how the universe has expanded over time. It works like placing identical measuring sticks across the cosmos and checking how their size changes with distance. If the universe's expansion is accelerating, the distant rulers appear smaller than expected. If the expansion is slowing, they appear larger. This method is known as baryon acoustic oscillation analysis, and it has transformed the way cosmologists calculate distances. Unlike distance methods that depend on brightness, which can be affected by dust or other complications, baryon acoustic oscillations rely only on geometry. Using this approach, researchers have mapped the three-dimensional distribution of galaxies across billions of light-years. These maps reveal the structure of the cosmic web with unprecedented clarity, and they also reveal the presence of the KBC Void. When scientists analyze galaxy distributions in our local region and compare them with predictions from baryon acoustic oscillations, they see a clear deficit. The void appears as a region where the expected clustering scale differs from what is measured in more distant, average regions of the universe. This is exactly what we expect if we are inside a large underdense region. The baryon acoustic oscillation data provides independent confirmation of the void's existence, as well as estimates of its depth and size. Mapping this structure is not simple. Large galaxy surveys like the Sloan Digital Skies Survey and the Baryon Oscillation Spectroscopic Survey have collected the positions and redshifts of hundreds of thousands of galaxies. Extracting the acoustic signal requires complex statistical analysis to distinguish the characteristic clustering scale from random variations in galaxy distribution. The signal itself is subtle, only a few percent stronger at that specific scale, but modern surveys are precise enough to detect it even from within the void. Galaxies inside the KBC Void show redshifts that are slightly higher than expected for their distances. This indicates a mild outward flow of matter caused by the lower density of the region. These measurements provide additional support for the void model and show that the Hubble tension appears across multiple independent methods, not just in supernova observations. The precision of baryon acoustic oscillation measurements continues to improve. Newer instruments, such as the Dark Energy Spectroscopic Instrument, are mapping tens of millions of galaxies with greater accuracy than ever before. Within a few years, the structure of the void and its velocity field will be mapped to within a few percent. This level of precision will help determine whether the void fully explains the Hubble tension or whether additional new physics is required. Measurements of the cosmic microwave background also support the presence of the void. The cosmic microwave background, which fills the universe with faint radiation from the Big Bang, has an almost uniform temperature of 2.7 Kelvin. The temperature differences are extremely small, only a few millionths of a degree, but they contain information about the early universe. When this radiation travels through a massive void, it experiences the integrated Sachs-Wolf effect. As photons pass through a region with lower density, they gain a small amount of energy when entering and lose a slightly different amount when exiting because the void is expanding. This results in a very slight temperature decrease. Astronomers have identified large voids in the nearby universe and compared the cosmic microwave background temperature in their direction. On average, the temperature is about 10 millionths of a degree cooler in those regions. This correlation matches theoretical predictions and confirms that voids leave measurable imprints on the cosmic microwave background. For the KBC void, the effect should be stronger because of its size. The radiation from the cosmic microwave background passes through nearly its entire extent before reaching Earth. Another interesting feature is the well-known cold spot in the cosmic microwave background. It is an unusually large and cold region on the sky. Some researchers suggest that a supervoid along that line of sight could be responsible for part of this temperature anomaly. Although the cold spot void does not align with the KBC void, it demonstrates how large underdense regions can create measurable effects on the microwave background. Current data shows that the KBC void's expected impact is subtle but consistent with observations. These temperature measurements also limit how extreme the void can be. If the void were significantly deeper or larger, it would create a more noticeable temperature signature that would already be visible in the data. The fact that no such extreme feature exists supports the current estimates, roughly a 20% density deficit extending about 1 billion light-years. The cosmic microwave background therefore provides a crucial independent check on the void's properties. Large cosmic voids like the KBC void also raise questions about the behavior of gravity on very large scales. Einstein's general relativity has successfully explained many astrophysical observations for more than a century. It predicts how stars orbit, how light bends around massive objects, and how the universe expands. However, the size and depth of the KBC void pushed the limits of what the standard model of cosmology typically produces in simulations. Some researchers suggest that a void as large as the KBC void might not naturally arise under general relativity paired with cold dark matter. This idea has led to alternative theories, such as modified Newtonian dynamics, or MOND. MOND proposes that gravity behaves differently at extremely low accelerations, which occur on the outskirts of galaxies and at cosmological distances. In this model, gravity becomes slightly stronger than expected, allowing structures to form more efficiently. As a result, simulations based on MOND can naturally produce larger voids without requiring unlikely initial conditions. However, MOND faces challenges. It struggles to match the precise temperature fluctuations in the cosmic microwave background that the standard model explains accurately. It also has difficulty accounting for the amount of gravitational lensing observed in galaxy clusters. These issues suggest that even if MOND explains some features of large-scale structure, it may not be a complete replacement for general relativity. Hybrid models attempt to combine MOND-like behavior with additional components, such as a small amount of hot dark matter in the form of neutrinos. These models can match both the cosmic microwave background data and the enhanced formation of large structures. Other modified gravity theories introduce additional fields or extra dimensions, altering gravity's behavior only at very large distances while keeping general relativity accurate on smaller scales. At present, no single theory explains everything. The debate continues between those who support modified gravity and those who prefer the standard model with the assumption that we simply live in an atypical region of the universe. Future surveys and velocity measurements across voids may help distinguish between these possibilities. The existence of large voids also affects estimates of the universe's age. The current age derived from the cosmic microwave background is about 13.8 billion years. This age relies on the cosmic expansion rate and other cosmological parameters measured from early universe data. However, the local expansion rate measured within 2 billion light-years is higher. If this local measurement represents the true global expansion rate, the universe would be younger, closer to 12.7 billion years old. This creates tension with observations of very old stars. Globular clusters appear to be nearly 13 billion years old. These ages are calculated from well-established models of stellar evolution. Stars evolve at predictable rates depending on their mass. By observing which stars have left the main sequence in a cluster, astronomers can estimate the cluster's age. The ages remain consistent across many clusters. The Gaia spacecraft has improved these measurements by providing accurate distances, reducing the uncertainties significantly. White dwarf cooling times provide another method for estimating ages, and they also indicate ages close to 12 to 13 billion years. These measurements are based on simple physics and are independent of cosmic expansion. If the universe were only 12.7 billion years old, many of these stars would appear older than the universe itself, which is not possible. This conflict suggests that the higher local Hubble constant does not represent the expansion of the entire universe. Instead, it is likely influenced by the KBC void. Some researchers argue that stellar ages could be slightly overestimated, but the required corrections would need to be large and systematic across multiple methods, making this unlikely. Others suggest that dark energy might evolve over time, slowing the early expansion and accelerating later, but this idea remains speculative. The age measurements from stars within our galaxy should not be affected by the void because they do not depend on cosmic expansion. They depend only on nuclear fusion and stellar physics. This means that the consistency of stellar ages with the age from the cosmic microwave background strengthens the case that the local Hubble constant is biased by our environment rather than indicating a younger universe. The behavior of galaxies inside and around the void provides additional clues. Galaxies are not stationary. They move through space in response to gravitational forces from surrounding structures. These motions, known as peculiar velocities, vary depending on the density of the region. On small scales, peculiar velocities can reach a few hundred kilometers per second. But when averaged across large regions, these motions should cancel out if the universe is homogeneous on large scales. Observations show otherwise. There are significant, coherent bulk flows of hundreds of kilometers per second extending out to roughly 300 million light-years. These flows are larger and extend farther than standard cosmology predicts. Simulations incorporating the KBC void reproduce these observed flows. Matter inside the void experiences a gentle outward push towards surrounding denser regions. The predicted velocities match observations well, including both the direction and magnitude of the flows. Without the void, the observed flows would be difficult to explain. If future observations reveal even larger scale flows, it could indicate that standard cosmology needs modification. If the flows diminish beyond the void, it would confirm that the KBC void is responsible. Current data shows that the flow weakens beyond a few hundred million light-years, supporting the void model. Another important structure in the universe is the Eridanus supervoid. While the KBC void surrounds our local region, the Eridanus supervoid lies several billion light-years away and is associated with an unusually cold region in the cosmic microwave background known as the cold spot. This supervoid is estimated to be nearly as large as the KBC void, with a density deficit of around 20 to 30%. The cold spot was first detected by the Wilkinson Microwave Anisotropy Probe and later confirmed by the Planck satellite. It appears as a region about 10 degrees across on the sky and is significantly cooler than the surrounding areas. A void of the size and depth of the Eridanus supervoid can account for part of this temperature deficit through the integrated Sachs-Wolf effect. The remainder may be due to statistical variation in the early universe or measurement uncertainty. Although the Eridanus supervoid does not align with the KBC void, it demonstrates that extremely large underdense regions can exist and can influence cosmic microwave background measurements. If multiple supervoids of comparable scale are confirmed, this may indicate that such structures are more common than previously expected, or that our models of structure formation need refinement. As cosmic surveys improve and map the universe more deeply, astronomers will gain better insight into how common large voids are. If they turn out to be rare, the KBC void becomes an even more unusual feature. If they are common, it may point toward underlying physical processes not fully captured by the standard cosmological model. The presence of the KBC void also affects measurements of the Hubble constant, which describes the rate of cosmic expansion. Observations show that local measurements of the Hubble constant using nearby supernovae and other distance indicators yield values around 73 km per second per megaparsec. However, measurements that rely on distant objects or the cosmic microwave background yield lower values, around 67 km per second per megaparsec. The boundary where these measurements begin to converge lies roughly 2 billion light-years away, close to the edge of the KBC void. This suggests that local measurements taken inside the void are biased by its underdensity. As a result, astronomers have introduced the concept of the Hubble bubble, a region in which the measured expansion rate is higher due to local environmental effects. If this bubble exists, it implies that to measure the true expansion rate of the universe, astronomers must look beyond the boundaries of the KBC Void. This requires observing supernovae and other distance markers at greater distances, which becomes increasingly challenging due to their faintness. New telescopes, such as the James Webb Space Telescope, are beginning to make these distant observations possible. Current data shows a trend consistent with the bubble model. The measured Hubble constant decreases as the distance of the observed objects increases. Beyond 2 billion light-years, the measurements approach the lower value predicted by the cosmic microwave background. While uncertainties remain, this trend strengthens the case that the local environment influences our measurements. Bulk flow measurements also support the idea of a local overestimation. Large-scale galaxy flows extend out to a few hundred million light-years and then decline, matching the expected behavior if the KBC Void is responsible for the local deviation. Baryon acoustic oscillation measurements show discrepancies primarily at low redshift, again consistent with local effects. All of these independent observations point in the same direction. Our local region appears to be unusual compared to the universe at large. Accepting the Hubble bubble hypothesis means acknowledging that many of our most precise measurements are biased by our location inside the void. This idea is not philosophically comfortable, but it helps reconcile multiple tensions in cosmology. The structure of the void also affects galaxy formation. In dense regions of the universe, galaxies frequently interact, merge, and evolve rapidly. These environments create galaxy clusters containing hundreds or thousands of galaxies, along with hot, X-ray emitting gas and active galactic nuclei. Inside voids, the situation is different. The low density means fewer interactions and fewer mergers. Galaxies evolve more slowly, retaining their gas for longer periods and continuing star formation over extended timescales. As a result, void galaxies tend to be smaller, bluer, and richer in gas compared to galaxies in dense clusters. Massive galaxy clusters do not form inside voids because the gravitational forces are too weak to pull enough matter together. The intergalactic medium inside voids also remains cooler and less disturbed than in dense regions. Without large clusters or strong gravitational activity, the gas does not heat up to extreme temperatures. This makes voids excellent environments for studying gas that resembles the early universe, including neutral hydrogen that can be detected through radio surveys. Because massive structures cannot form inside voids, these regions remain stable and evolve slowly. Dark energy accelerates this process by causing voids to expand faster than dense regions. Over time, voids become emptier, and the contrast between voids and filaments grows more extreme. The cosmic web becomes increasingly defined, with dense regions forming sharper structures and voids becoming even more empty. Understanding our position inside a large cosmic void also raises deeper questions about how we interpret the universe as a whole. Many cosmological measurements assume that we observe the universe from a typical location. This assumption is known as the cosmological principle, which states that the universe is homogeneous and isotropic on large scales. In simple terms, it means that the universe should look roughly the same from any location. The existence of the KBC Void challenges this idea. While the universe may still be homogeneous on the largest possible scales, local regions like ours can have significant deviations. These deviations influence our measurements of expansion, structure formation, galaxy distribution, and even cosmic microwave background properties. This does not mean that cosmology is wrong, but it does mean that local effects must be carefully accounted for when interpreting data. The Hubble tension highlights this issue clearly. Measurements taken inside 2 billion light-years show a higher expansion rate than those taken outside this region. If we do not correct for the void's influence, we may incorrectly conclude that new physics is needed to explain the discrepancy. However, once void effects are included, the tension is reduced, and the measurements become more consistent. Similar issues arise with large-scale bulk flow measurements. Without considering the void, the observed flow speeds appear too high for standard cosmology. When void effects are included, the predictions match observations. As our understanding of the KBC void improves, the agreement between theory and observation becomes more coherent. The impact of the void extends to galaxy evolution as well. In dense environments, galaxy interactions play a significant role in shaping structure. In voids, the lack of interactions leads to different evolutionary paths. This means that conclusions drawn from studying galaxies in dense regions cannot always be applied to galaxies in voids. Understanding this variation allows astronomers to build more accurate models of galaxy formation across different environments. The KBC void also affects dark matter and dark energy studies. If voids distort local measurements of expansion, then estimates of dark energy density and dark matter distribution must account for local deviations. Without this correction, cosmologists may overestimate or underestimate the influence of these components. The KBC void serves as a natural test region to validate cosmological models under different density conditions. Another area of interest is the behavior of gravity inside voids. If modified gravity models make different predictions from general relativity inside underdense regions, voids provide an ideal testing ground. Precise measurements of galaxy velocities, gravitational lensing, and structure formation inside the KBC void can help distinguish between competing theories. Observations that strongly favor one model over another could guide future developments in theoretical physics. The void also influences the interpretation of cosmic timelines. Stellar ages, white dwarf cooling times, and the formation history of galaxies all depend on the local environment. Because these measurements do not rely on cosmic expansion, they remain stable regardless of the void. This stability provides an anchor for cosmology, ensuring that the estimated age of the universe is grounded in local astrophysical processes that are unaffected by large-scale underdensities. Understanding the KBC void therefore provides a more complete picture of the cosmos. It shows that the universe is not perfectly uniform on all scales and that local structures can significantly affect observational data. By carefully separating local effects from global trends, astronomers can build a more accurate and reliable model of the universe. The study of voids also highlights the importance of large-scale mapping projects. As instruments become more advanced and capable of measuring millions of galaxies, our understanding of cosmic structure becomes increasingly detailed. Future surveys will allow astronomers to identify more voids, measure their sizes, and compare them with theoretical predictions. The distribution of voids will play a key role in testing cosmological models and improving our understanding of the universe's large-scale behavior. As data continues to improve, the role of the KBC void in cosmology will become clearer. Whether it fully explains the Hubble tension or only contributes to it, its impact on cosmic measurements cannot be ignored. Studying this void allows cosmologists to refine their methods and ensure that they interpret the universe in a way that accurately reflects its structure. The long-term future of cosmic voids is shaped mainly by dark energy. Dark energy causes the expansion of the universe to accelerate over time. As this acceleration continues, regions with lower density, such as voids, expand faster than regions with higher density. This means that voids grow larger and emptier as the universe ages. In the present-day universe, voids already occupy most of the cosmic volume. The filaments and clusters form a relatively small fraction of the overall space. As dark energy becomes more dominant, this contrast increases. Filaments thin out, clusters become more isolated, and voids expand into the surrounding regions. Galaxies inside voids will experience increasing isolation. Today, a galaxy inside the KBC void can still observe surrounding filaments, clusters, and distant structures. The light from these objects reaches us after traveling across billions of years. However, as dark energy accelerates expansion, distant structures will eventually cross the cosmic horizon. Once they cross this horizon, their light will no longer reach us. They will effectively disappear from view. Over tens of billions of years, the number of visible galaxies will steadily decline. The cosmic microwave background radiation will also fade. As the universe expands, the wavelengths of its photons stretch, becoming longer and weaker. Eventually, the cosmic microwave background will redshift to wavelengths so large that it becomes undetectable. A civilization living far in the future, inside a void galaxy, would have a very different view of the universe. They would not see the cosmic web. They would not detect the cosmic microwave background. They would observe only their local group of galaxies, which remain gravitationally bound. This would make reconstructing the true history of the universe extremely difficult. Inside the KBC Void, the Milky Way and the Andromeda Galaxy will merge in about 4 billion years. The resulting galaxy, sometimes called Milkomeda, will dominate the local group. Other nearby galaxies will remain bound for some time, but eventually, even they will drift too far away to be observed. Star formation in these galaxies will gradually decline. Galaxies consume their gas over time, and without new gas inflows from the cosmic environment, star formation slows down and eventually stops. Over tens of billions of years, the galaxies will consist mainly of old stars, white dwarfs, neutron stars, and black holes. On even longer timescales, hundreds of billions to trillions of years, stars will exhaust their nuclear fuel. New stars will rarely form. The universe will enter a period dominated by the remnants of stellar evolution. Black holes will become the most massive objects in existence. As time progresses further, gravitational interactions between stellar remnants can slowly eject them from galaxies. Over extremely long timescales, galaxies will gradually evaporate, leaving behind only a scattering of stars and black holes drifting through space. Eventually, even black holes will begin to evaporate through Hawking radiation, a quantum mechanical process that causes them to lose mass. This evaporation takes extraordinarily long periods, far longer than the current age of the universe, but it is expected to occur. In the final stages, the universe will become increasingly empty. Matter will be distributed sparsely across immense distances. Photons will stretch to extremely long wavelengths. Temperature differences will smooth out. The universe will approach a state often described as heat death, where no structures remain and no significant physical processes occur. Voids will be a major contributor to this future. As they expand, they accelerate the separation between structures. Over enough time, voids dominate cosmic geometry. Their growth ensures that isolated pockets of matter will drift farther and farther apart, with communication and travel between them eventually becoming impossible. This far future scenario highlights how important voids are in shaping cosmic evolution. They are not simply empty regions but active participants in the universe's long-term development. Their expansion, combined with dark energy, determines the ultimate fate of galaxies, star formation, and cosmic structure. As our understanding of the KBC Void continues to improve, astronomers are gaining clearer insights into how voids fit into the broader structure of the universe. Voids are not isolated anomalies. They are natural components of the cosmic web. Matter in the early universe collected into filaments and clusters, leaving large regions with lower density between them. Over billions of years, these underdense regions expanded faster than their surroundings, forming the voids we observe today. The KBC Void is unusual mainly because of its size and because we happen to be located inside it. Most voids are smaller and do not significantly affect local measurements. The KBC Void, however, is large enough to influence several independent cosmological observations, including redshift measurements, bulk flows, baryon acoustic oscillations, and local estimates of the Hubble constant. Ongoing surveys continue to map the three-dimensional distribution of galaxies inside and around the void. These maps show how galaxies are distributed within the underdensity and how they transition into surrounding filaments. As instruments improve, astronomers will be able to construct more detailed models of the void's geometry, measure its boundaries more accurately, and understand how it formed. Explaining the formation of such a large void remains an active area of research. Some simulations using standard cosmology can produce underdensities of this size, but they are rare. Modified gravity models can create large voids more easily, but these models struggle to match other observations. Future work will help determine whether the KBC void represents a statistical anomaly or whether it points toward new physics. Another important aspect of void research is understanding how voids influence the flow of matter. Matter inside a void experiences less gravitational pull from nearby structures. As a result, galaxies within the void tend to move outward toward denser regions outside it. This creates a characteristic velocity pattern that can be measured using redshift-independent indicators. The velocity field within the KBC void aligns well with predictions from void models, strengthening the case that the void is real. As new data becomes available, these measurements will improve, allowing cosmologists to test competing theories more precisely. Voids also provide opportunities to study dark energy. Because gravitational forces are weaker in underdense regions, dark energy's influence becomes easier to detect. Observing how the void expands and how matter flows within it allows astronomers to test predictions about dark energy's behavior. If dark energy evolves or behaves differently in different environments, voids may reveal these subtleties. Large voids also influence the long-term evolution of galaxies. As voids expand and filaments thin out, galaxies inside them become more isolated. In the distant future, as dark energy accelerates expansion, galaxies inside voids will lose contact with the cosmic web. Eventually, only gravitationally bound groups will remain visible. Over long timescales, these groups will merge into single systems. Inside these isolated systems, star formation will decline as gas supplies are exhausted, and galaxies will become dominated by older stars and stellar remnants. This far-future vision highlights the role voids play in shaping cosmic evolution. While often described as empty, voids are dynamic components of the universe that influence the fate of galaxies and the structure of space. The study of voids also reveals how interconnected cosmological measurements are. The Hubble constant, galaxy distributions, cosmic microwave background variations, and large-scale flows all relate to void structure and evolution. Understanding these connections helps cosmologists refine their models and resolve long-standing tensions. The KBC void also affects how we interpret signals from distant galaxies and quasars. Light from these objects travels through the void before reaching us, influencing redshift measurements. As telescopes observe more distant and faint objects, correcting for void effects becomes increasingly important. Future missions such as the Vera C. Rubin Observatory, the Euclid Telescope, and the Nancy Grace Roman Space Telescope will map billions of galaxies across large volumes of the universe. These surveys will identify new voids, measure their shapes, and allow comparisons with theoretical models. They will help determine whether the KBC void is rare or whether similar structures exist elsewhere. Studying voids also helps refine understanding of the cosmic microwave background. Voids leave subtle imprints on temperature and polarization patterns. Measuring these more precisely can test theories about inflation, structure formation, and dark energy. The KBC void demonstrates that our cosmic environment plays a significant role in shaping what we observe. Accounting for its influence ensures cosmology remains accurate. It also highlights the importance of exploring regions beyond our local environment to gain a complete understanding of the universe. In the end, the KBC void challenges assumptions about uniformity and cosmic evolution. It reminds us that the universe is not perfectly smooth and that our observations are influenced by where we are located. By studying this void, we gain a deeper understanding of our cosmic neighborhood and the universe as a whole. The KBC void is not simply a gap in the cosmic web. It is a key to understanding expansion, galaxy distribution, dark energy, and the future of cosmic evolution. Its study continues to refine our picture of the universe and will guide future research as astronomers explore deeper questions about the cosmos and our place within it.